Good morning, team. In this opportunity, I'm going to present my final project, which is the application of GD&T in a motor mounting plate. And my name is Eduardo Romero. This project applies GD&T principles to an electric motor mounting plate, verifying the position of the keyholes under maximum material condition MMC and least material condition LMC. The proper use of GD&T improve the interchangeability, reduce manufacturing errors, and also cost because companies they don't need to fabricate extra devices until get the real one. So in this situation, I prepare a model that represents how it's going to be the plate for this kind of electric motors. I would like to mention that the application of these plates are usually made in electric motors and also conveyors too. Okay, so this plate is represented by three holes mainly. The main one is where the shaft is going through, and the hole for this is 100 millimeters with an LMC of 0.5. So also it has a flatness of 0.5 in the primary dating feature, which is A. Also it has an angularity of 0.5 in the primary dating feature, letter A. It has also a profile of surface around the whole model, so it's around the primary, secondary, and tertiary dating feature. For the small holes, these basically are small or supporters, where the screws basically gonna go through, and it's going to provide a more empotration in the plate. So this has an 18 millimeters per hole with an MMC of 0.5, respecting to the primary, secondary, and tertiary dating feature. It's the same for the 4 holes, which is 2 right here, and sorry, 1 1 1 1 equals 4. It has a perpendicularity sorry, of 0.5 respecting to A and B in the tertiary dating feature. And finally, the general dimensions for this model, it's 500 width and length, but for the purpose of this project I just made it in the scale of 1/10. So details of the project. As I mentioned, it has a nominal hole of 100 millimeters, applied position tolerance of 0.0 millimeters, depending of the situation or depending of the condition of the hole. It's going to be represented by an MMC or LMC. As a small example, if this hole will be as an MMC, I have to subtract 100 millimeters minus 0.5, and vice versa. If I want to apply LMC, which is in this situation, I need to add 0.5 size tolerance. So for the purpose of this project, I put measured deviations of 0.3 millimeters for the X label, and for the Y axis 0.4. So just a summary, or as a result, we can get that the X deviation for the shaft hole, which is the main one, it's 0.25, and the Y deviation is 0.15. making an actual position, which I use the formula of x squared plus y squared, everything to the 0.5, and it made me the value of 0.58, which is in an allowed position because it's less than the allowed, right? And I tried to do the same process for the 4 holes, and unfortunately with the deviations I put it at the beginning of 0.3 and 0.5, I could conclude that the holes 4 and 5 cannot pass the test, and for this situation the manufacturer or the engineer has to propose another methods to try to clean or improve these rejections. So yeah, as we can see here, what I did, it was I tried to place it in the graph, and as we can see here in the first 3 holes, the test was approved, so it's accepted. But unfortunately for the holes 4 and 5, which is 4 and 5, which is this couple 2 holes right here, unfortunately they couldn't pass. So what can we do for this situation? Well, we can start to improve or think in another manufacturing methods which will be more accurate and could improve this mistake in the process of the factoring in this of this model. And yeah, this is my project. Thank you so much, team, and yeah, this is it. Thank you so much.